So, uh, I want you to just think about the sunlight hitting your face right now.
Yeah, it's such a common feeling.
Right, like when you step outside on a clear afternoon, you just feel that warmth. Your first instinct is to think of it as something, immediate.
Oh, absolutely. We're taught that light takes about 8 minutes to travel from the surface of the sun to the Earth.
Exactly. And I mean, that part is true. But the actual energy, the heat, the photons that are actually warming your skin, they didn't originate on the surface.
Not even close, yeah.
That energy was forged in this like crazy nuclear furnace deep in the core of our star before modern humans even walked the Earth.
It's wild.
Neanderthals were literally wandering around while the exact light hitting your face today was slowly and agonizingly fighting its way out of the sun's interior.
It is just a profound realization of cosmic timescales, right? And it immediately kind of shatters this comforting illusion we have about our star.
Yeah, the illusion that it's just this peaceful, glowing orb.
Right, because from down here, the sun looks like a quiet, perfectly still, basically eternal heat lamp painted on the ceiling of the sky.
We literally build our seasons and, our entire agriculture around its constancy.
We do, but the reality is completely the opposite. It is a violently vibrating, churning, just continuously changing sphere of superheated plasma.
And tearing open the architecture of that chaotic sphere is our mission for today's deep dive.
Yes, it is.
We are taking this foundational astrophysical research paper. It's titled Solar Interior Structure and Luminosity Variations. And we're going to extract the actual mechanisms that make our local star tick.
Step by step.
Exactly. And I'm talking directly to you, the Class 12 student listening to this right now. You're in the middle of studying classical mechanics, thermodynamics, electromagnetism.
All the heavy hitters.
Yeah, you are learning the rules of the physical universe. So today, we're going to take those exact rules and apply them to the ultimate cosmic laboratory.
Because if you can understand the mechanics of the sun, you basically hold the blueprint for understanding almost every other star in the observable universe.
That's the perfect way to frame it. Now, this source paper, I'm not going to lie, it's incredibly dense.
Oh, it's heavy reading. It's packed with the kind of high-level astrophysics that typically hides behind massive walls of academic jargon.
Right. But the underlying physics, the actual mechanisms driving the star, they're deeply intuitive once you just break them down.
Right. So we're going to examine the sun from the inside out. We'll explore the static structure that keeps it from just collapsing, the dynamic variations that cause its brightness to fluctuate, and the frankly unbelievable methods scientists use to actually peer inside a blinding ball of gas 93 million miles away.
Okay, so let's start with the architecture itself. The source paper, it immediately grounds its analysis in something called the standard solar model.
Right, the standard solar model.
Now, my initial thought when I hear the word model is visual, right? I picture a plastic cutaway globe in a science classroom, or maybe a 3D computer simulation showing all the glowing layers.
Yeah, that's the standard assumption, but in the context of this paper, that's not what astrophysics means at all.
It's not a physical representation.
No, not at all. In astrophysics, the standard solar model is purely mathematical. It is a really comprehensive framework of differential equations.
Oh, wow. Okay, so just pure math.
Pure math. These equations are designed to calculate the fundamental properties of the sun's plasma at literally any given depth, from the absolute center all the way up to the visible surface.
Okay, so when you say fundamental properties, what exactly are these equations solving for? What are the variables?
Primarily, they're calculating 4 intertwined variables. That's mass, pressure, temperature, and chemical composition.
Mass, pressure, temperature, composition.
Oh, right. The idea is that if you pick a specific radius, say, exactly halfway between the core and the surface, the mathematical model should be able to tell you exactly how hot it is right there.
So it's like sticking a theoretical thermometer in.
Exactly. And it tells you how much pressure is pushing outward, how much mass is pressing downward, and whether the plasma at that specific spot is mostly hydrogen or helium.
That's crazy. It's essentially a massive mathematical spreadsheet of the sun, just built layer by layer.
That's a great way to think of it. A layer by layer spreadsheet.
Okay, I can visualize that. A giant set of equations balancing out. But what is the bedrock principle holding that math together?
Yeah.
Because, the sun is a ball of gas with a mass roughly 330,000 times that of the Earth.
It's massive.
Yeah. And all of that mass generates a colossal gravitational field. Gravity is relentlessly trying to pull all of that matter toward the exact center, right?
That's what gravity does best.
So why doesn't the sun just collapse under its own crushing weight? Like, what is stopping it?
That is the foundational question of stellar physics. I mean,
Yeah.
if gravity were the only force operating, the sun would just free fall into itself and collapse into this tiny, ultra-dense sphere in roughly half an hour.
Wait, half an hour.
That's it. Yeah, just about 30 minutes and it's gone. But it doesn't. It remains totally stable for billions of years. And this brings us to the core concept holding the standard solar model together, which is hydrostatic equilibrium.
Hydrostatic equilibrium. Okay, let's unpack the physics there, because those are words that definitely show up in Class 12 fluid dynamics.
Let's break it down.
So hydro usually means water, but here we're talking about a fluid. And the sun, being a superheated plasma, actually behaves like a fluid, right?
Exactly. Plasma is a fluid.
And static means stationary, like it's not accelerating.
Right.
And equilibrium means a net force of zero. All the forces acting on the fluid are perfectly balanced.
That is the exact translation. Perfect. Hydrostatic equilibrium is this mathematical state where the inward crush of gravity is perfectly, flawlessly balanced by an equal and opposite outward force.
And in the case of the sun, what is that outward force?
That outward force is thermal pressure.
Thermal pressure. So heat pushing outward.
Yes. Extreme heat and radiation generated deep within the star. Every single layer of the sun is caught in this massive, high-stakes tug of war.
The weight pushes down, the heat pushes up.
Precisely. The weight of all the layers above pushes down, while the immense pressure of the hot gas below pushes up.
Okay, I'm trying to picture this physically. Let's use an analogy. If I inflate a rubber balloon, the rubber itself is stretched tight, right?
Right.
The elasticity of the rubber is constantly trying to snap back and squeeze inward, trying to, collapse the balloon.
Yes.
So that elastic squeeze is acting like gravity. It wants to pull everything to the center.
The analogy, yeah.
But the air molecules that I blew inside the balloon, they're bouncing around, they're hitting the walls, exerting an outward air pressure against the inside of the rubber. And as long as the outward air pressure matches the inward squeeze of the rubber, the balloon holds its shape perfectly.
That analogy works really well to understand the opposing forces. But to truly grasp the sun's equilibrium, you have to scale that balloon up to 1.4 million kilometers across.
Okay, that's a big balloon.
Yeah, and you replace the rubber with the gravitational pull of 2 octillion tons of mass.
2 octillion tons.
And then you replace your breath, the air pressure, with the blazing radiation of a nuclear furnace.
Right. Just slightly more intense than a party balloon.
Just a bit. And furthermore, this balance isn't just happening at the edge like the rubber of a balloon. It is happening continuously at every single microscopic point throughout the entire volume of the star.
Okay, so wait. The pressure has to be higher in the center, right?
Yeah.
Because the very center is supporting the weight of the entire star above it, whereas a layer near the surface only has to support the tiny little bit of gas above it.
Precisely. You nailed it. As you move deeper into the sun, the accumulated weight of the gas above you increases drastically.
Just like swimming deep in the ocean, the pressure builds.
Exactly. So to maintain equilibrium and not collapse, the thermal pressure pushing back must increase at the exact same rate. This means the temperature and density must absolutely skyrocket as you approach the center.
Which leads us directly into the first major layer of our internal map, right?
Yeah.
The engine room of the solar interior, the core.
The core, yes.
Because, gravity is just a property of mass, that's a given. But to understand the other side of that tug of war, the immense thermal pressure pushing back, we have to understand where that heat actually comes from.
We do.
So we are plunging roughly 700,000 kilometers deep, straight into the center. What are the conditions actually like down there, according to the mathematical model?
The conditions in the core stretch the absolute limits of human comprehension. We are looking at temperatures reaching roughly 15 million Kelvin.
15 million degrees.
Yeah, and the pressure required to maintain that equilibrium,
Yeah.
it is crushing. The density of the core is around 150 grams per cubic centimeter.
Okay, put that in perspective for me. 150 grams per cubic centimeter.
To put that in perspective, that is roughly 150 times the density of liquid water, or nearly 10 times the density of solid lead.
10 times denser than lead. Wait.
Yeah.
If you compress matter that tightly, wouldn't it solidify? Like 10 times denser than lead sounds like a solid block of metal.
Right, on Earth, absolutely yes. But at 15 million Kelvin, the kinetic energy of the particles is so extreme that they just cannot bind together to form a solid structure.
Oh, because they're moving too fast.
Exactly. The heat literally rips the atoms apart. You don't have intact atoms with, nice little electrons orbiting a central nucleus.
The electrons are gone.
They're completely stripped away. What you have is a highly compressed, just roiling soup of free-floating atomic nuclei, which, in the case of hydrogen, are just bare protons and a sea of free electrons zipping around them.
So this is plasma.
Yes.
Yeah.
This state of matter is a high-density plasma.
Okay, so a super dense, super hot soup of positively charged protons. And this extreme environment is what allows the sun's engine to ignite. The source paper identifies this specific mechanism as nuclear fusion.
All right.
And more specifically, the proton-proton chain.
Yes, the proton-proton chain is the primary sequence of nuclear reactions that powers stars the size of our sun. Fundamentally, nuclear fusion is just the process of forcing lighter atomic nuclei together to form a heavier nucleus, which releases a massive amount of energy in the process.
Oh, it's mashing things together.
Exactly. Here, the sun is basically taking 4 individual hydrogen protons and fusing them to create one single helium nucleus.
Okay, I want to stop here. I need to put on my class 12 physics hat here because there is a massive conceptual roadblock in what you just said.
Oh, what's that?
Well, hydrogen nuclei are just protons, right?
Right.
And protons have a positive electrical charge.
Yes, they do.
But one of the most fundamental laws of electromagnetism is that, charges repel. 2 positive charges want to violently push away from each other. It's like trying to force the north poles of 2 really strong magnets together.
You literally can't do it with your bare hands.
Exactly. So if the core is just a soup of protons, how in the world do they ever fuse? Doesn't standard electromagnetism dictate that they should repel each other long before they ever touch?
That is the exact problem that absolutely stumped astrophysicists for decades in the early 20th century.
Really? So it's a known paradox.
Oh, yeah. You have correctly identified the Coulomb barrier. It's an immense, invisible wall of electromagnetic repulsion. In a normal environment, protons would violently bounce off each other before getting anywhere near close enough to fuse.
So how do they get close?
Well, to get them to stick together, you have to bring them so incredibly close that the strong nuclear force can take over.
The strong nuclear force.
Right. Which is incredibly powerful, but it only operates at unimaginably short distances. Once they are close enough, it binds them. But getting them that close is the trick.
So how do they get that close? I'm assuming the 15 million degree temperature has something to do with it, right? Heat is just kinetic energy. So the particles are just moving insanely fast.
That is part of the answer, yeah, but it's not the whole story. At 15 million Kelvin, these protons are indeed flying around at staggering speeds.
Right.
You might assume they're moving so fast that when they speed toward each other, they can just power through that electromagnetic repulsion by sheer brute force.
Like 2 cars driving towards each other so fast that even when they hit the brakes, their momentum just carries them into a collision anyway.
Exactly. They just smash through the repulsive barrier. That's the logical assumption.
But let me guess, that's not what happened.
No, it's not. Here is where classical physics completely breaks down. When you do the math, taking into account the average kinetic energy of a proton at 15 million degrees, it turns out they still aren't moving fast enough.
Wait, really? 50 million degrees isn't hot enough?
Not even close. According to classical thermodynamics and electromagnetism, the Coulomb barrier is simply too high. The protons should just bounce off each other. Fusion should be impossible, and the sun should not shine.
Okay, my mind is slightly blown. If classical physics says the sun shouldn't shine, what piece of the puzzle is missing? Because obviously, the sun is shining. I felt it on my face this morning.
The missing piece is quantum mechanics.
Oh boy, here we go.
Specifically, a really bizarre phenomenon known as quantum tunneling.
Quantum tunneling. Okay, I've heard the term in sci-fi movies, but let's break down the actual mechanism for a physics student. What is actually happening?
Okay, so in the subatomic realm, particles like protons do not act like solid billiard balls with exact fixed locations.
Right.
According to the Heisenberg uncertainty principle, a proton's position is actually described by a wave of probability. It basically exists in a haze.
So they don't have a hard physical edge. They're sort of smeared out in space.
Yes, exactly. Smudged or smeared out. And because they are smeared out, when 2 protons approach each other, their probability waves interact with that repulsive Coulomb barrier we talked about.
Okay. Yeah.
And there is a tiny, infinitesimal, but not zero mathematical probability that a proton approaching the barrier will simply find itself on the other side of it.
Right.
It doesn't climb over the wall. It doesn't smash through the wall. It literally tunnels through the barrier, instantly transitioning to the other side where the strong nuclear force can just grab it.
That sounds like actual magic. A particle just teleporting past an impenetrable wall because its probability wave happens to overlap the other side.
It is entirely counterintuitive to our daily experience, yes, but it is a fundamental reality of quantum mechanics.
That's insane.
But here's the catch. The probability of this happening for any two colliding protons is astonishingly low. It is so rare that a single proton in the sun's core might bounce around, colliding with other protons, for several billion years before it finally successfully tunnels and fuses.
Wait. Billions of years? I thought the core was this raging, instantaneous inferno of nuclear explosions.
Yeah, that's a common misconception. It's actually a surprisingly slow burn on the scale of an individual atom.
Okay, so if it's so rare, how does the sun produce enough energy to not collapse?
Because the core contains an unfathomable number of protons, literally octillions of them, and they are colliding billions of times a second. So that astronomically rare tunneling event is actually happening constantly across the entire volume of the core.
Oh, I see. It's just a numbers game.
Exactly. It's a numbers game. Trillions of successful fusions happen every single second, just because there's so much material providing a steady, continuous output of energy.
Okay, so quantum tunneling allows the protons to finally fuse into helium. But how does that actually create the energy that fights gravity? I know the paper details the energy output, but let's walk through the conservation of mass. We are combining 4 protons to make 1 helium nucleus.
Let's do the accounting.
Yeah, let's balance the books.
If you were to take a highly precise, theoretical scale, and you weigh the 4 individual hydrogen protons before the reaction, and then you weigh the single helium nucleus that gets produced after the fusion.
You expect them to weigh the same.
You would, but you would find a discrepancy. The final helium nucleus actually weighs about 0.7% less than the 4 protons that went into making it.
Okay, but a core tenet of classical physics is that matter cannot be created or destroyed.
Right.
Where did that 0.7% of the mass go? Did it just vanish?
It wasn't destroyed, it was fundamentally transformed.
Yeah.
That tiny fraction of missing mass, what we call the mass defect, was converted entirely into pure energy.
Ah.
And the conversion rate is governed by probably the most famous equation in physics,
Oh.
Albert Einstein's E equals mc squared.
Right. Energy equals mass times the speed of light squared.
Yeah.
Let's really look at what that equation means in this context for our Class 12 listeners.
Good idea.
The m in that equation is that tiny 0.7% of missing mass. But the c is the speed of light, which is already a massive number, 300 million meters per second.
Exactly. And the equation demands that you square that massive number.
So you're multiplying that tiny little missing mass by 9 times 10 to the 16th power.
Yes. Which means that even a microscopic fraction of a gram of matter contains an absolutely devastating amount of latent energy.
Wow.
To sustain its hydrostatic equilibrium, the sun's core converts roughly 4 million metric tons of physical matter into pure energy every single second.
4 million tons of physical mass vanishing from the universe every single second, replaced by just pure radiation.
Yep.
And that is the thermal pressure. That is the heat pushing outward against the crush of gravity.
Yes, exactly. The energy is released primarily as high-energy gamma-ray photons, along with subatomic particles called neutrinos.
Which brings up a really, really vital speculation.
Yeah.
I mean, if the core is effectively a localized region where millions of tons of matter are detonating into pure energy continuously, if it's acting like millions of hydrogen bombs going off every second, why doesn't it just blow the sun apart? We talked about equilibrium, but this sounds incredibly volatile. Yeah. What stops a runaway chain reaction from just shredding the star?
It's a highly logical concern. I mean, a runaway reaction is exactly what happens in a supernova.
Right.
But our sun is stabilized by a brilliant built-in thermodynamic thermostat that perfectly regulates the fusion rate. And it relies entirely on the interplay between gas pressure and gravity.
Okay, I love a good feedback loop. How does the thermostat work? Let's say for a moment that the fusion rate in the core accidentally spikes. Like too many protons tunnel at once and it generates a surge of extra energy. What happens next?
Okay, so if the energy surges, the temperature in the core increases.
Makes sense.
And when a gas or plasma heats up, its thermal pressure increases, it pushes outward harder.
Right. And because it's pushing outward harder than gravity is pulling inward,
Yeah.
the core would actually physically expand, wouldn't it? It would puff up slightly.
Exactly, it expands. But here is the critical thermodynamic principle. As a gas expands, it cools down.
Oh.
By pushing outward against gravity, the plasma expends energy and its temperature drops. As the core cools, the protons slow down. With slower protons, the rate of quantum tunneling decreases. And so, the fusion rate naturally drops back down to normal.
That's brilliant.
Yeah.
And I'm guessing it works in reverse too, right?
Walk me through it.
So if the fusion rate slows down too much, the core cools, the thermal pressure drops. Suddenly, gravity has the upper hand, so it compresses the core.
Yes.
And compressing a gas heats it up, the protons speed up, tunneling increases, and the fusion engine revs back to life.
You have just flawlessly described negative feedback. It is a beautifully self-correcting mechanism. The core of the sun is basically on a continuous multi-billion-year cruise control, constantly making these microscopic adjustments to its size and temperature to maintain that perfect hydrostatic equilibrium.
That's incredibly elegant.
Isn't it?
So we have a complete picture of the engine room now. Gravity squeezes, quantum tunneling allows protons to fuse, mass converts to energy via E=mc², and the whole thing self-regulates through expansion and contraction.
That's the core.
The result is this massive flood of high-energy gamma-ray photons radiating outward from the center. But the paper makes it really clear that this energy doesn't just shoot straight out into space. The journey from the core to the surface is actually a grueling process because the photons have to travel through the next mammoth layer of the internal structure, which is the radiative zone.
Right, the radiative zone. This surrounds the core and extends about 70% of the way to the sun's surface.
Okay.
In this deep interior, the primary method of heat transfer is radiation, meaning the energy is carried directly by those photons we just talked about. Their goal is simple: travel outward at the speed of light and escape the star.
Given that light travels at 300,000 kilometers per second, you'd think that journey would be nearly instantaneous, like boom, out.
It would be if the radiative zone were empty space. But this zone is unimaginably dense plasma. And to understand why the photons struggle so much, we need to dive deep into a really critical vocabulary term from the source literature, which is opacity.
Opacity. Okay. In daily life, opacity is just the opposite of transparency, right? A clean glass window has low opacity, light passes right through. A thick brick wall has high opacity, light is blocked.
Exactly.
So if the plasma have high opacity, it means it's resisting the passage of light.
Precisely. And in the radiative zone, the opacity is driven by the fact that the plasma is completely jammed full of tightly packed free-floating electrons and positively charged ions.
Wait, why do free electrons cause high opacity? Like, why are they blocking the light?
Because of a process called Thomson scattering.
Thomson scattering.
Yeah. When a high-energy gamma-ray photon tries to travel outward, it almost immediately crashes into one of these free electrons. The photon's electromagnetic field interacts with the electron's charge. The photon actually gets absorbed, momentarily agitating the electron, which then immediately re-emits a new photon to shed that excess energy.
Okay, so the photon is absorbed and re-emitted.
Yeah.
But does the new photon just keep moving outward on the same path?
No. That is the absolute crux of the problem. When the electron re-emits the photon, it does so in a completely random direction.
Oh, no.
Yeah. It might shoot it sideways, it might shoot it diagonally, it could even shoot it straight back downward toward the core.
Wow.
Furthermore, the environment is so densely packed that a photon can only travel a fraction of a millimeter, what physicists mathematically call its mean free path, before it crashes into another electron and the whole process repeats.
So it moves a millimeter, gets absorbed, gets fired out randomly, moves another millimeter, gets absorbed, gets fired randomly, over and over. I'm trying to visualize this. It's like being trapped in a pinball machine, but way worse.
Way worse.
Let me try an analogy. Imagine you are standing exactly in the center of a massive enclosed superstadium.
Okay, I'm picturing it.
The stadium is packed shoulder to shoulder, wall to wall, with literally millions of people, and everyone, including you, is totally blindfolded.
A very chaotic, terrifying environment.
Extremely. So your goal is to walk from the center of the field to the exit gates at the far edge. But because you are blindfolded and the crowd is so dense, every time you take a single step, You violently bump into someone,
Right.
you bounce off them, you spin around, you get completely disoriented, and your next step is in a totally random direction. You might step toward the exit, you might step sideways, or you might step right back to where you started a minute ago.
That is an excellent, excellent conceptualization of what physicists mathematically define as a random walk.
A random walk.
Yes. The photon is not taking a straight path. It is taking trillions upon trillions of tiny, jagged, unpredictable steps.
But if your steps are truly random, you spend most of your time just wandering back and forth over the same small area. It must take forever to actually make any forward progress toward the exit. How long does this journey actually take for a single photon?
The math behind a random walk dictates that the total distance traveled from the starting point is proportional to the square root of the number of steps taken.
Okay.
Because the mean free path, the step size, right, is so incredibly microscopic. A photon must undergo a staggering number of collisions. Estimates vary depending on the specific path, but it takes a single photon anywhere from 100,000 to upwards of 1,000,000 years to finally escape the radiative zone.
1,000,000 years.
Yes.
Let's just pause and let that sink in for a second. Light travels from the moon to the Earth in about 1 second.
Yep.
It takes light 8 minutes to travel the 93 million miles from the sun's surface to the Earth. But it takes 1,000,000 years just to travel a few 100,000 kilometers from the inside of the sun to the outside layer.
That is the astonishing reality of high opacity and Thomson scattering. The photon might travel billions of miles back and forth, ping-ponging in the dark, just to make a few thousand kilometers of actual outward progress.
That's exhausting just to think about.
It is, and during this 1,000,000-year random walk, as it constantly collides and interacts, the photon slowly loses energy.
Oh, it does.
Yeah, it starts in the core as a lethal, ultra-high energy gamma ray. But by the time it finally reaches the edge of the radiative zone, it has lost enough energy to become a slightly less intense X-ray or ultraviolet photon.
So after this agonizing million-year journey through the densely packed stadium, the photon finally reaches the outer edge of the radiative zone. But the paper indicates that something drastic happens here. The method of heat transport suddenly completely changes. Why? What shifts in the environment?
Well, as we move further and further out from the nuclear furnace at the center, the plasma naturally begins to cool down.
Right, further from the fire.
Exactly. It drops from 15 million degrees in the core down to roughly 2 million degrees at the boundary of the next layer.
Only 2 million.
Chill. Right, relatively speaking. But this cooling triggers a fundamental phase shift in the atomic structure, which actually causes the opacity to absolutely skyrocket even more. And this initiates the final structural layer, which is the convection zone.
The convection zone. Okay, let's explore this boundary. Why does a drop in temperature cause opacity to skyrocket? You mentioned earlier that in the core, the intense heat rips electrons away from their nuclei.
Exactly. Deep down, everything is fully ionized. It's just free particles. But as the temperature drops to only 2 million degrees, the heavier atomic nuclei elements like carbon, oxygen, and iron that exist in trace amounts in the sun, they slow down just enough that they can begin to recapture some of those free-floating electrons.
Oh. So they start to become bound atoms again.
Yes, they rebuild themselves.
Okay, so the electrons are snapping back into orbit around their nuclei. But why does a bound electron block light better than a free electron? I'm struggling with the mechanics of that. I mean, a particle is a particle, right? Why does being in an orbit make it a better shield?
It's a really great question, and the answer lies in quantum energy states. A free electron can scatter a photon, like we talked about with Thomson scattering, but it doesn't easily absorb all of its energy.
Okay.
However, an electron bound to an atom exists in specific, rigid energy levels, kind of like rungs on a ladder.
Right, basic chemistry.
Exactly. When a photon with just the right amount of energy comes along, that bound electron acts like a perfect catcher's mitt. It absorbs the photon entirely, using its energy to literally jump up to a higher rung on the ladder.
Oh, I see. So the presence of intact atoms turns the plasma from this hazy, scattering fog into a highly efficient absorption sponge. The photons are literally just swallowed up.
Precisely. The plasma becomes incredibly opaque. It's no longer just a crowded stadium. It's a solid brick wall. The photons get completely trapped. They can no longer slowly diffuse outward through a random walk.
But wait, if the radiation can't get through, that heat is just going to build up at the bottom of this opaque layer, right? I mean, the nuclear engine in the core isn't stopping. It's constantly pushing energy outward.
It never stops.
So if that energy hits a wall and builds up, wouldn't the thermal pressure rapidly spike? And just blow the outer layers of the sun completely off?
It absolutely would if radiation were the only mechanism allowed by physics to transport heat. The system requires a release valve, and the universe provides a brilliant alternative driven by fluid dynamics, which is convection.
Convection, yes. We learned about this in high school chemistry and earth science. It's the transfer of heat through the physical movement of a fluid.
Exactly. Since the light can no longer carry the heat through the matter itself physically moves to carry the heat. The opaque plasma at the very bottom of the convection zone absorbs all that trapped radiation, and as it absorbs the heat, it naturally expands.
As we discussed with the core's thermostat, when a fluid expands, its density decreases.
Right. It becomes less dense and therefore more buoyant than the cooler plasma resting above it. So massive pockets of this superheated buoyant plasma physically detach and begin to rise violently toward the surface.
Just floating up.
Right. They carry the trapped heat with them, traveling all the way up through the convection zone to the visible surface of the sun, the photosphere.
And once this hot material reaches the surface,
it is finally exposed to the transparent vacuum of space. The plasma releases its heat, radiating it away as the visible sunlight that eventually reaches Earth.
That's the light that hits our face.
That's the one. And having dumped its energy, the plasma at the surface cools down. It becomes denser and heavier, and so it sinks back down deep into the convection zone to be heated all over again.
It's a continuous churning cycle. Hot material rises, cold material sinks. The classic analogy here is a pot of thick soup or heavy oatmeal cooking on a stove.
Oatmeal is perfect.
Right, because the heat from the burner can't just shine through the thick oatmeal. Instead, the oatmeal at the bottom gets superheated, forms a bubble, and violently pushes its way to the surface. It bursts at the top, releasing a puff of steam, the heat, and then the cooler oatmeal rolls back down the sides of the pot.
That is exactly what is happening in the outer envelope of the sun, but on a terrifying scale.
Yeah.
The entire outer 200,000 kilometers of the sun is a boiling, churning pot of plasma.
Wow.
And we can actually see evidence of this. If you look at high-resolution telescope images of the sun's surface, it isn't smooth at all. It has a mottled, grainy texture called granulation.
Right, I've seen those pictures. It looks almost like a honeycomb or a cobblestone street.
Yeah, each one of those cobblestones is the top of a convection cell, a massive column of boiling plasma rising from below.
How big are we talking?
Well, a single standard granule is roughly the size of Texas.
Texas, one little bubble.
One bubble. And there are deeper, larger convection currents called supergranules that are actually larger than the entire planet Earth. Just imagine Earth-sized bubbles of boiling plasma continuously rolling to the surface.
That is an image that will stick with me. Earth-sized bubbles of nuclear oatmeal. So we have now fully mapped the static interior structure presented in the standard solar model. We have gravity balanced by thermal pressure. We have the core fusing hydrogen via quantum tunneling. We have the radiative zone where ancient photons take a million-year random walk. And we have the convection zone acting as a boiling release valve at the surface.
That comprises the complete structural blueprint of our star.
But the title of the research paper we are unpacking is Solar Interior Structure and Luminosity Variation.
Exactly. The variation.
We've established the structure, now we have to tackle the second half. Because all this violent boiling and fusing implies that the total energy output isn't perfectly steady. Does the sun actually flicker or change its brightness?
It does indeed. When astrophysicists use the term luminosity, they are referring to the total amount of energy, the absolute sum of all light and radiation that the star emits into space in every direction. And the source literature extensively explores how and why this total output fluctuates.
Okay, let's break down these luminosity variations. How drastically does the brightness change, and over what timelines?
The paper divides these variations into two entirely distinct temporal categories. First, there are evolutionary variations, which occur gradually over billions of years. And second, there are dynamic variations, which occur on much shorter timescales of months, years, or decades.
Let's start with the long-term billion-year picture.
Yeah.
Why would the sun's baseline brightness change over evolutionary time?
To understand that, we have to look back at the engine room, the core. As we discussed, the sun is fundamentally a machine that converts hydrogen into helium. But that helium doesn't go anywhere.
It just sits there.
Yeah. Over the last 4.5 billion years, as the core has tirelessly fused protons, it has slowly been filling up with helium ash.
Okay, so the chemical composition of the core is fundamentally changing over time. It's getting less hydrogen-rich and more helium-rich. How does that affect the hydrostatic equilibrium we spent so much time on?
It changes the balance significantly. A core packed with helium is chemically denser than a core made of pure hydrogen. And if the core becomes denser, the mass is more tightly packed, which means the gravitational pull inward actually becomes slightly stronger.
Oh, and if gravity is pulling harder, the core should start to collapse.
Exactly. But to prevent collapse and maintain equilibrium, the core responds the only way it can. It generates more thermal pressure to push back harder against the increased gravity.
And the only way to generate more outward pressure is to run the nuclear engine hotter.
Precisely. The core slowly, gradually contracts a tiny fraction, which drives the temperature even higher. This higher temperature causes the protons to slam together faster, increasing the rate of quantum tunneling, which accelerates the fusion reaction.
So it's constantly revving up.
Yes. The net result is that over billions of years, as the core accumulates more helium ash, the sun is forced to burn hotter and brighter just to keep itself from collapsing.
That implies that the sun today is actually noticeably brighter than it was when the solar system first formed.
Significantly brighter. It is estimated that the sun is roughly 30% more luminous today than it was 4 billion years ago.
30%. That's a huge difference.
It is. And a billion years from now, it will be even brighter still. That is the evolutionary, inescapable trajectory of a main sequence star.
Okay, so that's the slow burn. But the paper also details dynamic variations changes happening on human timescales. When I think of the sun changing over years, the first concept that comes to mind is the 11-year solar cycle.
Right, the 11-year cycle.
We hear about it constantly on the news, periods of solar maximum where there are solar flares and solar minimum where things are quiet.
The 11-year solar cycle is the absolute primary driver of short-term luminosity variations, and the entire cycle is dictated by a massive complex system called the solar magnetic dynamo.
Okay, how does the magnetic field dictate how bright the sun is, and why does it operate on an 11-year cycle?
To understand the cycle, we have to look at how the sun physically moves. Unlike the Earth, which is a solid sphere of rock that rotates as one single cohesive unit, the sun is a ball of fluid plasma. Because it is a fluid, it doesn't all rotate at the same speed. The plasma at the sun's equator is spinning significantly faster than the plasma near the north and south poles. This phenomenon is known as differential rotation.
Differential rotation.
Yeah.
So the middle is rotating faster than the top and bottom. How does that impact the magnetic field?
Well, imagine the sun's magnetic field starting out at solar minimum as a series of neat, straight, invisible lines running vertically from the North Pole down to the South Pole.
Okay, picturing it.
Because the equator is spinning faster than the poles, the highly conductive plasma at the equator literally grabs onto those magnetic field lines and drags them forward.
I can picture that. It's like taking a rubber band, holding the top and bottom still, and spinning the middle. The rubber band is going to get stretched and wound up tight.
That is exactly what happens over several years. The differential rotation stretches, pulls, and twists those magnetic field lines, winding them tightly around the sun's equator.
So it gets all tangled.
Highly tangled. The magnetic field becomes incredibly dense and stressed. Eventually, these localized bundles of twisted magnetic force become buoyant. They violently punch their way up right through the convection zone and burst out of the surface of the sun.
And when a twisted knot of magnetic force bursts through the surface, we see it, right? That is what creates a sunspot.
Yes. The intense magnetic field locally suppresses the convection we talked about earlier. It acts like a plug, preventing the boiling, superheated plasma from rising to the surface in that specific spot.
Oh, it blocks the heat.
Exactly. Because the fresh heat is blocked from coming up, that specific patch of the surface cools down. And because it is cooler than the surrounding boiling plasma, it appears black to our telescopes. That is a sunspot.
Let me stop you there, because this raises a very logical but perhaps confusing point regarding luminosity.
Let's hear it.
Sunspots are, by definition, dark patches on the surface of the star where heat is being blocked.
Right.
So, if we are in a solar maximum, the peak of the 11-year cycle, and the sun is absolutely peppered with dozens of these dark sunspots, shouldn't the overall total brightness of the sun go down? Shouldn't a spotted sun be a dimmer sun?
That is the exact assumption that logical intuition would lead you to. If you take a light bulb and paint black spots on it, the light bulb emits less total light.
Right.
But the source literature reveals a really counterintuitive, fascinating reality about solar physics. It is true that the sunspots themselves are cold and dark, and they do locally reduce the light output. However, The immense twisted magnetic activity that creates the spot doesn't just create a dark void.
What else does the magnetic knot create?
It creates sprawling surrounding networks of intensely heated, brilliant plasma called faculae.
Craculae?
Yes, the magnetic energy actually superheats the plasma around the edges of the sunspot. So wherever you have a dark spot, you are virtually guaranteed to have a massive glowing halo of faculae surrounding it.
Oh, that is fascinating. So it's a trade-off.
It is, but it's an unequal trade-off. It turns out that the extra intense radiation emitted by the bright faculae more than makes up for the light that is blocked by the dark sunspot. The bright areas drastically overcompensate.
Meaning the net total.
The net result is that during a solar maximum, when the sun's face is heavily scarred with dark sunspots, its total luminosity is actually slightly higher than during a solar minimum when the surface is completely pristine and blank.
That's amazing.
A more spotted sun is, somewhat miraculously, a brighter sun.
That is such a brilliantly counterintuitive physical reality. Yeah. And I want to tie this directly back to you, the listener. Why does a tiny variation in brightness over an 11-year cycle matter to you?
It's a great question to ask.
If you were studying environmental science alongside physics, you know that the Earth's entire climate system, the temperature of the oceans, the behavior of the atmosphere, our agricultural seasons, is balanced on the knife edge of the energy budget we receive from the sun.
Exactly. Even though the variation between a solar minimum and a solar maximum is incredibly small, amounting to roughly a 0.1% change in total solar radiance, that tiny fractional fluctuation represents a massive amount of absolute energy.
Right. 0.1% of a star's output is still astronomical.
Yeah.
And understanding these minute natural fluctuations in solar luminosity is absolutely crucial for modern science. It allows climatologists to precisely separate natural solar-driven climate variations from the effects of human-induced changes in Earth's atmosphere.
You have to know exactly what the star is doing to understand what the planet is doing.
It highlights the deep interconnectedness between astrophysics and Earth sciences.
It really does.
Okay, we have covered an immense amount of theoretical ground today. We mapped the 15 million degree core. We traced the million-year random walk of photons through the radiative zone. We explored the Earth-sized boiling convection cells. We discussed how twisted magnetic fields create faculae that alter the star's brightness.
We've built the whole model.
We have. But I have to address the elephant in the room.
Uh-oh.
As a Class 12 student, learning the scientific method, you were taught to demand proof. Hypothesis requires observation. Everything we've discussed so far sounds like an incredibly detailed, perfect mathematical story. But how on earth could scientists actually prove any of this?
That is the ultimate test of skepticism, and it's essential in science.
I mean, the sun is 93 million miles away. It's a blinding, unimaginably hot, boiling sphere of gas. We cannot send a physical probe into it. The metal would vaporize before it ever got close to the surface, let alone the core.
Oh, instantly.
We obviously can't drill a hole and take a physical core sample. So how can physicists assert with absolute mathematical certainty exactly where the radiative zone ends and the convection zone begins? How do we empirically prove the standard solar model?
The answer to that question is arguably one of the most elegant, ingenious triumphs of modern physics. It relies on a methodology heavily emphasized in the source literature regarding structural measurements. The technique is called helioseismology.
Helioseismology. Okay, let's break that word down.
Let's do it.
Helio means sun. Seismology, which we usually associate with Earth, is the study of earthquakes, or more accurately, the study of how mechanical waves travel through a physical structure.
Yes.
So we are talking about sunquakes. We are studying sound waves inside the sun.
Exactly. We are using acoustics to map the interior.
But wait, a fundamental rule of acoustics is that sound requires a medium to travel through. Space is a vacuum. Sound cannot travel through the vacuum of space. So how can there be sound waves? We can't hear the sun?
You are correct that sound cannot travel through the empty vacuum of space to reach our ears on Earth. We cannot hear the sun. However, sound can absolutely travel through the dense physical plasma inside the star itself.
Oh, because the plasma is a fluid medium.
Exactly. And to understand where these sound waves come from, we have to revisit the convection zone.
The boiling outer layer. The Earth-sized bubbles of plasma.
Yes. Think about the sheer mechanical violence of that convection process. You have billions of tons of superheated material relentlessly smashing its way up to the surface, bursting and plunging back down at supersonic speeds.
It sounds chaotic.
It is chaotic, it is turbulent, and it is unimaginably noisy. The turbulent convection acts like an endless series of acoustic explosions. The convection zone is constantly generating a deafening roar of low-frequency sound waves.
So the sun is essentially screaming continuously, just filled with a cacophony of internal noise.
That is a highly accurate description. Now, what happens to those pressure waves? They hit the surface, but they can't travel out into the vacuum of space.
Because there's no medium.
Right. So instead, they bounce. And many of these sound waves are directed downward, plunging deep into the interior of the sun.
Okay, the sound waves dive down into the deep interior. Do they just hit the dense core and bounce straight back like an echo?
Not quite. And this is where we connect directly to the wave mechanics you study in Class 12 physics.
Yeah.
You have likely learned about wave refraction.
Wave refraction, yes.
When a wave passes from one medium into another with a different density, or when the temperature of a medium changes, the speed at which the wave travels also changes.
Right. It's the same principle as light bending when it enters water, or, sound bending on a cold night over a lake because the air temperature near the water is different than higher up. When the wave's speed changes, its path bends.
Exactly. The physics of refraction apply universally. Inside the sun, as these sound waves dive deeper, they are moving through plasma that is getting dramatically hotter and denser with every kilometer.
Which changes the speed of sound.
Because the temperature is rapidly increasing, the speed of sound is rapidly increasing. And because the speed of the wave is constantly changing, the path of the sound wave isn't straight. It is continuously refracted. It bends.
Oh, I see. As it dives deeper into hotter plasma, the wave path curves more and more.
Yes. It curves so much that eventually, deep in the interior, the wave path forms a massive, smooth arc. It turns completely around and heads straight back up toward the surface. The sun is filled with millions of these acoustic waves, all diving to different depths, arcsing and returning to the surface.
And what happens when these returning sound waves finally hit the underside of the sun's surface?
When a massive internal pressure wave hits the underside of the surface, it physically pushes the plasma outward. The surface of the sun actually rises slightly.
Like a ripple.
Exactly. Then, as the wave passes, it falls back down. Millions of these waves are hitting the surface constantly. As a result, the very outer layer of the sun is continuously rippling, vibrating, and breathing in and out.
The entire star is shimmering with sound waves. I have two analogies to help visualize how scientists use this.
Oh, I'd love to hear them.
First, in medicine. This sounds exactly like how an ultrasound machine works. A doctor wants to see the structure of a baby inside a mother's womb, but obviously cannot use visible light. So the machine sends high-frequency sound waves into the body. Those waves travel until they hit different densities, fluid, tissue, bone, and they reflect or refract back out.
And the machine reads them.
Right. A computer measures exactly how long those echoes took to return and uses that data to map a perfect picture of the inside without ever making a physical cut.
That is a phenomenal, precise analogy. Through helioseismology, astronomers are basically performing a continuous spherical ultrasound on a star.
My second analogy is a bit more everyday. It's like when you go to the grocery store and you want to pick out a perfect, dense watermelon.
Oh, the watermelon type.
Yeah. You can't see inside the rind to know if it's ripe. So what do? You thump it with your hand. You listen to the thud.
Right.
The specific resonance, the pitch and vibration of the sound the watermelon makes, tells your brain whether the inside is hollow and dry or dense and full of water. You map the interior based entirely on how the acoustic waves bounced around inside it.
Tapping a watermelon perfectly captures the fundamental concept of acoustic resonance. The sun is basically acting as a massive, multi-layered resonant cavity.
Okay, but here's the practical challenge. We can tap a watermelon with our ear close by. How do astronomers actually measure the microscopic rippling on the surface of the sun from 93 million miles away? Like you said, we can't put a microphone on the sun.
No, we cannot use a microphone, but we can use light. And this brings in another fundamental Class 12 physics concept, the Doppler effect.
The Doppler effect, like when a police siren sounds higher pitched as it speeds toward you and lower pitched as it drives away because the motion is compressing or stretching the sound wave.
Exactly, that's the acoustic Doppler effect. But the Doppler effect also applies to light waves.
Oh, right.
Scientists use highly specialized satellite instruments to look at specific absorption lines in the spectrum of the sun's light. When a patch of the sun's surface is pushed upward toward Earth by an internal sound wave, the light from that specific patch gets slightly compressed.
So its frequency increases.
Yes. It shifts slightly toward the blue end of the spectrum.
A blue shift.
Exactly. And when that patch of the surface falls back down, moving away from Earth, the light stretches and shifts slightly toward the red end of the spectrum, a red shift.
Wow.
By continuously monitoring the surface, astronomers can observe millions of separate patches of the sun oscillating back and forth between blue shift and red shift.
That is absolutely unbelievable. So they're watching the entire surface of the star ring and vibrate like a giant bell just by looking at the color of the light shifting slightly back and forth.
It is an observational masterpiece. By carefully analyzing the exact frequencies of these millions of vibrations, essentially calculating the pitch of the ringing bell, physicists can work backward.
Because they know how waves work.
Right. Because the depth the wave reaches is determined by the speed of sound, and the speed of sound is dictated by the temperature and density of the plasma. The frequencies of the surface vibrations reveal the exact conditions of the interior.
So using the sound waves, they can calculate the exact temperature, density, and flow of the plasma at every single depth.
Yes, they used helioseismology to map the exact internal speed of sound, and from that data, they were able to pinpoint the precise depth where the radiative zone ends and the turbulent conduction zone begins.
And the ultimate question, when they finally used these acoustic echoes to map the inside of the sun, and they compared it to the standard solar model, that spreadsheet of complex differential equations we started with, did they match?
It was one of the most spectacular confirmations in the history of astrophysics. The empirical structural map generated by listening to the sunquakes matched the theoretical predictions of the mathematical standard solar model almost flawlessly.
That's incredible.
It proved that our fundamental understanding of hydrostatic equilibrium, opacity, and nuclear physics was undeniably correct.
That is just the ultimate triumph of physics. I really want that to sink in for our listener. By applying the exact same basic rules of fluid pressure, quantum states, wave refraction, and the Doppler effect that you calculate in your Class 12 textbook with a pencil and paper.
The exact same rules.
Humanity has managed to peer inside a blinding, boiling nuclear furnace millions of miles away and flawlessly map its internal organs. We know precisely what is inside a star, purely through the power of mathematics, observation, and physics.
It serves as the ultimate proof that the laws of physics are universal. The equations that describe how a balloon holds its shape or how sound bends over a lake are the exact same equations that govern the thermonuclear fires of the heavens.
So let's bring this incredible journey to a close. We have achieved our mission today. We started with the mathematics of the standard solar model.
We did?
We balanced the crushing force of gravity perfectly against the thermal pressure of nuclear fusion to achieve hydrostatic equilibrium. We plunged into the core to watch protons tunnel through quantum barriers to forge helium and release energy. We traced the agonizing million-year random walk of a photon battling the opacity of the radiative zone.
A long journey.
Very long. We rode an Earth-sized bubble of superheated plasma through the convection zone. We untangled the differential rotation and magnetic dynamos to discover why a spotted sun is a brighter sun. And finally, we used the Doppler effect to watch the entire star ring like a bell, proving every single piece of the theoretical puzzle to be true.
You have now thoroughly unpacked the core structure and dynamic variations of a star. You hold the blueprint.
It is a massive amount of physical theory, but I hope we've made the mechanisms intuitive. Before we go, though, I want to leave you with one final, deeply provocative thought to mull over. Something to consider the next time you step outside, look up, and feel that million-year-old light on your face.
Let's consider the profound material connection between the physics of the solar interior and the listener themselves.
Precisely. Think about the journey of matter. The light illuminating the room around you was forged in the unimaginably hot center of the sun eons ago. But the physical connection goes much deeper than light. Look at your own hand.
Right.
Think about the heavy elements that physically make up your biology, the iron carrying oxygen in your blood, the calcium fortifying your bones, the carbon forming the foundation of your cellular DNA.
All of it.
Those complex, heavy elements could not be created in the relatively cool 15 million degree core of our current sun. The proton-proton chain stops at helium. To fuse heavier elements like carbon and iron, you require temperatures not of millions of degrees, but of billions of degrees.
Temperatures that are only achieved in the dying, catastrophic collapse of stars far more massive than our own.
Exactly. Those elements in your blood and bones were forged in the cores of ancient, massive, giant stars that lived out their lifespans, burned through their fuel, lost their hydrostatic equilibrium, and exploded in spectacular supernovas long, long before our sun or the Earth ever existed.
We are quite literally stardust.
That's stellar debris. That's stardust. Drifted across the cold vacuum of space for eons. It eventually clumped together under gravity, ignited to form our solar system, cooled to form our rocky planet, and over billions of years of biological evolution, eventually formed you.
It's an incredible lineage.
So when you studied the intricate, boiling, fusing interior of a star using your Class 12 physics, you aren't just looking up at some distant, detached alien object in the sky. You're looking backwards in deep time. You are studying the blueprints of the factory that built the very atoms you are currently using to think. You are looking into a cosmic mirror.
Which is just a staggering perspective.
It raises a final question. By studying physics, by learning how the stars work, are we simply the universe's way of finally waking up and trying to understand itself?
A truly profound thought to end on. Keep studying the physics. Keep questioning the mechanics. Keep looking deeper.